And now you start getting a little nasty, and in addition to having errorless training with reward, you also punish it on a nearby wavelength. Well, what happens? What happens is called peak shift and behavioral contrast. Okay? The peak shift means that the wavelength you like the most now is shifted away from the punished wavelength. And you like it more, that's the behavioral contrast, then you liked the color on which you've been rewarded. So this is something you've never been rewarded on. You like it more than something on which you've been rewarded. Well, you might say, well, I can understand part of that. You know, I can understand that if I take this excitatory gradient from reward and now I put in an inhibitory gradient from punishment, if I subtract the gradients, I'm going to get a peak shift. Okay, that's just these Gaussians we were talking about. But it's a net, and therefore it's smaller. But now I say, okay, we're talking about a return on center off surround net. It's self-normalizing. The area under this curve tends to be preserved. Since this is narrower, its peak shoots out higher. So this is an example of total activity normalization in operant conditioning. And I think it's also a philosophical interest, because if we ask, do we know what we like in this life? Imagine now a complicated cognitive map with rewards and punishments all over the place. And imagine these things are shifting. Well, you don't know what you're going to like the most, so it might be something that you never experienced. Okay, well now what about behavioral contrast in time? Now I want to shift to language. Okay, so it's a huge leap, but I want to point out to you it's really the same thing. So here the question is, how do you design a working memory to code temporal order information in short-term memory before it's stored in long-term memory? And this comes up in speech, language, sensory motor control, cognitive planning. We'll come back to it later. So what is a working memory? It's the kind of thing where I say, repeat the following telephone number. So I say 723-8842, go dial it. Then I trip you, you fall on your face. I say, go dial it. You say, I can't. You distracted me. That's working memory. You can store it for a little while. I distract you, it's gone. Okay. Well, what is one of the main issues here? One of the main issues is that temporal order short-term memory is often imperfect. Okay. So for example, free recall. In free recall, I might show you a list of items. And your job is now to write them down in the order in which you think of them. And one of the problems is that the probability of recall and the order of recall are not veridical. You tend to remember things at the beginning and end better than in the middle. And you tend to recall things at the beginning and the end earlier than things in the middle. Well, why is this such a mess? Well, I claim that these errors are consequences of a deeper adaptive design, which I call the long-term memory invariance principle. So what's the heuristic here? The heuristic is trivial. The heuristic is it doesn't pay to store anything in working memory if you can't learn about it. Because otherwise, a list would seem novel no matter how many times it was experienced. So what point is to do that? And so what the long-term memory invariance principle says is something very, very simple. That working memories are designed so that storage of new items in short-term memory doesn't disrupt the long-term memory memories of previously stored items. So if you put in new stuff and it washes away everything you know from memory, you're done for. So we put in the stability requirement. The main thing isn't that this is subtle. The main thing is to think about short-term memory in the context of long-term memory. You have to be willing to make that leap. So what's an example? So I want to preserve the long-term memory of familiar words like myself and elf when I'm storing a new word like myself in short-term memory in order to learn it in long-term memory. You can't take for granted that when I store this for the first time, I'm not going to wash out all of my present memories of the parts if I already learned them. You cannot take it for granted. So my claim is the stability of temporal order in long-term memory implies the non-veridical storage of temporal order in short-term memory. The claim is the brain thought it was more important for you to be able to remember stuff than it was for you to be able to store infinitely long lists in short-term memory. You could only store short lists in short-term memory. So let me dramatize this with some pictures. So let's say my was into short-term memory, goes through an adaptive filter, it's categorized. Self was in short-term memory, it goes through an adaptive filter, it's categorized. This is all now familiar. Now my self comes into working memory for the first time. I don't want to recode the long-term memory of my and self. That would be a disaster. I could never have language. So how do we solve this problem? Well, I believe it's solved by using what I like to call item and order working memories. The first property we already know. You're going to have a content addressable item code, so the items are going to just be stored by their activity. The second property I claim is that temporal order is also stored as relative sizes of item activity. So we're doing what we did in space a minute ago, but now we're doing it in time. So the claim is that if I have more activity, that I'll be the first one. If I have a little less activity, I'll be the second one. If I have still a little less activity, I'll be the third activity. So temporal order is stored in relative sizes of item activities. Well, if you're going to believe that you're going to be storing this through an on-center, recurrent on-center, you got to worry about the noise saturation dilemma again. So that suggests that you really have a recurrent on-center off-surround network. And I claim that's really the answer. That if you have a shunting on-center off-surround network that automatically normalizes your activity, that's going to give you the kind of behavioral contrast in time that explains a lot of data about working memory. So you might start out by saying, how would the brain discover something so sophisticated as a working memory? You can't expect evolution to be too smart. My claim is it just adapted an ancient design, namely an on-center off-surround network. So let me just say this a little more definitely. Given a sequence of events, R1, R2, blah, 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 every subsequence of that is a sequence in its own right, which could be coded. So the question is, how do you encode past subsequences, like the first n items, in short-term memory, so that the short-term storage of future subsequences from n plus 1 on, first, doesn't erase prior learning of these events in the past, and second, it's possible that future events will reduce the importance of past events as the future context forces. We can't prevent that. So that this invariance principle does something very simple. It chooses short-term memory activities so that newly stored activities can alter the size of old activities without recoding their long-term memory patterns, and it does it as follows. New events do not change the relative activities of past event sequences, but they may reduce their absolute activities. Well, why do we want this constraint? Well, that's because if you have a bottom-up adaptive filter that obeys a dot product, i.e., where you have your activities here multiplied by your adaptive weights and added up, then the relative sizes of inputs to these coding nodes, if I take xi and just shunt it down by a relative amount, that's going to leave the relative sizes coming up to the coding nodes preserved, so the relative importance of any code will be preserved even if I'm shunting down past activities by future activities. So let me give you the simplest example of that just so you can see what I mean. Suppose at time 1 I just activate a given node. Then at time 2, when I bring in the second activity, I shunt it down, but I normalize. So the total is 1. The third activity, let's say I shunt it down again, and I shunt this down again. When I bring in the third activity, it adds up to 1 again, and I keep multiplying the past by the same thing. In this way, at every stage, I have normalization, but in addition, all I'm doing is keeping the relative sizes of the past preserved. Well, if you do that, and if you have strong inhibition, then the claim is that you can't have veridical storage. You're going to get a bow in this simple case where you have doubly greater than a half at 2. Okay? So you can have a primacy gradient, you could have a bow that turns into a recency gradient. And you can generalize this. You don't have to have those rules. You can say U sub I is the attention paid to the ith item when you present it. So when I present the first item, I give it a certain amount of attention. I present the second item, I give it a certain amount of attention, and I shunt the first item down by a certain amount. And I keep going, giving everything their own amount of attention and shunting them by some arbitrary factor. Well, then the total strength of short-term memory is just the sum of these at each time. Okay? So the shunt implies that the total strength is that expression. But normalization, which is a property of shunting networks, implies that the total activity is going to go up to some activity that is going to be conserved. This is like the limited capacity of working memory. So that's some law like this, something that goes up to this limit m. And in fact, it's known, there's data, you might know this old data by Kahneman and Beatty, that pupil diameter is going to change as a function of working memory load. You can see it change like that. Well, if you put these two equations together, you can solve everything, and you can prove that for short lists, you'll have a primacy gradient. Primacy gradient means you're going to rehearse things in their correct order, or you can have just a recency gradient. The most important thing is the most recent, or you can have a bow. So the claim is that you're not always going to have veridical storage, and in fact, it's known, for example, in free recall, that you don't have veridical storage. So if you want to go further with this kind of thing, you can show that a bow can occur at any position in these models. It's a design constraint. And I'll call the position where it occurs the transient memory span. And in my earlier work, it was convenient to make it occur at about 4. And those of you who know Nelson Cowan's recent work on the magical number 4, that's what you should think of. And the immediate memory span is the short-term memory plus the readout from long-term memory. That's a little bigger, and for those of you who know George Miller's classical work on the magic number 7, that's what you should think about there. But the point I'm trying to make is I haven't taught you everything that one might want to know about short-term working memory, but this can thrust you into that field with a firm foundation. Okay. In fact, you can also define such networks dynamically, and work with Gary Bradsky and Gail Carpenter. This just shows simulations, I won't go into that now, of recency gradients and bows which you can put anywhere you want as part of your design. But you can also generalize it in order to store sequences with repeats and such things. So this I can't go into today, but this thrusts you into that kind of situation. Well, given that you have these patterns being stored, the question is how do you get them out of there? And the claim is there's readout by a non-specific rehearsal wave. So these things are just reverberating in there. It's a non-specific rehearsal wave when you give the volitional command, you don't know what's being stored. And the claim is that the largest activity is the first one out. And then you also need the idea that when something comes out, it self-inhibits so that you don't have perseveration. So the biggest one won't always be coming out, out, out. And this has become quite standard too now. You might know the work of Oman and Koch on this in the mid-80s. Okay, so in summary, the claim is that you can have a primacy gradient for short lists, above, and a recency gradient for longer lists, and these immediately help you to explain the probability and order that you're getting free recall, and you can think of it as a form of behavioral contrast in time. Now, this is again a huge field, and there's much development and data predictive success since the 70s. Many people now like calling this competitive cueing, and in fact now the neurophysiology has caught up. This slide is from a talk Dan Bullock gave recently, and there's some beautiful work from the Georgopoulos lab in prefrontal cortex, data collected during cued recall figure drawing tasks, where these kind of cell profiles are exactly what you would expect to get from this kind of working memory model. So now we can start comparing neurophysiological data with these more formal models. But as has been the case in a lot of situations, these data are from 2002, and the basic models were introduced in the 70s, and there's been a lot of work subsequently. Now, I should say that there have been many specialized nets discovered by quite a few workers over the years that can now be viewed as variations on a theme. But here, it's important now to ask, why do all of these cases have this CAM property? Why do they all converge to one of infinitely many equilibrium points? And when won't they converge to equilibrium points? When will they go into some kind of oscillatory dynamics? And so, to start this going, we need to ask, under what conditions does a neural network always approach one of possibly infinitely many equilibrium points, which you can think of as stored memories, in response to an arbitrary but sustained data pattern? And then when you violate these conditions, can you classify lots of other kinds of dynamics, including traveling waves, bursts, standing waves, chaos, etc.? And in my own work, this program began in the 60s and 70s for both long-term memory and short-term memory. And I want to just give you an overview of some examples because, again, they'll show how you can bring together lots of different data, and they give you great power in thinking about complex systems at this time. I also want to show it to you because there's a lot of work that still needs to be done. I would say, we're just at the beginning of having a true theory. So we'll be talking about competitive and cooperative systems. So in general, what's a competitive system? That's a system where on the right-hand side of the equation, if you increase the activity of the jth state, you can only decrease the rate of change of the ith state. And in a cooperative system, if you increase the activity of the jth state, that increases the rate of change of the ith state. And there are many open problems here for people who are interested in the quantitative side of things. But I want to give you an introduction into classifying competitive systems, if only because it's really a fun kind of theory, but also helps you to get some real power here. Everything I've shown you before is a special case of what I'm about to say. So let's take an n-dimensional system. You have the ith activity changing through time with some nonlinear function of all the activities. It's competitive. If you increase the jth activity, the ith rate of change can only go down. Well, how do you classify biologically useful ones? Well, we're talking competition here, and so I claim that one way to do it is keep track of who's winning. It's a competition, track the winner. And more seriously, the claim is that every competitive system induces a decision scheme, and you can embed a series of discrete decisions into a continuous competitive system where these decisions are decision hypersurfaces that are very far from equilibrium. What do I mean by those big words? All I mean is when you're looking at a competitive system, you want to track where are the most noticeable changes. So this guy starts to grow a lot. Then this guy starts to grow a lot. Then this guy starts to grow a lot. Keep track of that. And we say that the system jumps when a new winner emerges. So this guy was growing fastest, now this guy's growing fastest. Jump, 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 jump. Track the jumps. They're local decisions. And moreover, you've got to pump energy through the system to keep it going. And it turns out that there's a Lyapunov functional here that I won't say more about, but that led to a lot of global Lyapunov function theorems later on, which pumps the energy through the system. So let me give you a feel for how it works in the next couple of minutes. So we rewrite the competitive system as a non-negative amplification function, like here in the Volterra-Latke system with just xi. And then the rest of it is the competitive thing, which if you increase the jth or kth variable, you pull it down. So you just rewrite it that way for convenience. And then let me tell you what I mean by tracking the winner. First, there's a property called positive ignition, which you can prove just using the chain rule. You want to look at the biggest competitive right-hand side. Look at the maximum of all those right-hand sides. And you want to say if the max is bigger than 1 at any time, then the max will be bigger than 1 at all times. So what does that mean? That means if any variable starts growing, then some variable will always grow. So you ignite the competition, and once it ignites, it just goes, goes, goes. And so this is a kind of positively invariant region. If you look at the set of states where the max is non-negative, call it R plus, if you get into here, you can never leave it. Now, if you can't get into there, that means that the max isn't non-negative. Well, if all of these right-hand sides are non-positive, then everything just settles down. It just converges. It just crashes. The competition never got started. So either you just converge to decreasing values here, or something interesting happens there. Well, you also have negative ignition, which you look at the minimum right-hand side. And if that's ever negative, then it's always negative thereafter. It means if some variable ever starts decreasing, there will always be a variable that's decreasing. So that means if the system ever gets into this region where the maximum is non-positive, it can't get out. Well, what if it doesn't get in there? That means the minimum is positive. That means everyone increases to limits. So inside here, something more interesting can happen. And so we now have these two invariant regions, R plus and R minus, and all the action is going to be going on in their intersection. Okay. And inside here, what the jumps say is keep track of the maximal variable. So let's say my jumps look like this. I jump from here to here, 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 here to here. Well, that starts looking like an oscillation. And so you classify all the possible jumps to prove sustained oscillations if you have cycles of jumps, or you converge. If you don't have jumps, you go down a jump tree, you run out of decisions, you converge. So it gives you a very vivid way of thinking about competition. And a classic example of that is due to May and Leonard. It's called the voting paradox, which got a lot of play in the 70s. We have three candidates or three cells. The first beats the second beats the third beats the first. So what happens when they all compete? Well, it's intransitive. You beat yourself. You just keep going and going. The system can't make up its mind. And they wrote this as a Volterra-Latka system, and they proved some theorems about it, where these competitive terms reify. 1 beats 2, 2 beats 3, 3 beats 1. But from their analysis, you really can't see what's going on. But if you look at the jump sets, well, here they are. You jump from 1 to 2, from 2 to 3, from 3 to 1. And you can just see, you got to keep going, you got to keep going. So it gives you a really nice geometrical understanding of why this competitive system can never settle down. But there are other competitive systems that you can make very, very general that always settle down. And one example of this is what Mo Hirsch, when Mo read these theorems, he liked calling them the ABC systems, because there's A, there's B, and there's C. It's sort of a no-brainer. So how do these systems come in? Well, a classical example is a recurrent, narrow on center, broad off surround working memory network. And you can write this network as A, which is an amplification function, B, which is its signal function, and C, which is its adaptation level. Well, it includes many other examples. So, for example, you can have totally different inhibitory than excitatory signal functions and still converge. You can have an off-surround that includes everyone and still converge, and so on. But no matter how you design this thing, given any such system with an essentially arbitrary amplification function, an essentially arbitrary signal function, and an essentially arbitrary competitive adaptation level, which means that if I increase any variable, the adaptation level, remember the feed-forward case, this is the feedback version, the adaptation level can only increase, which means if you put a minus sign, you get increasing competition. Then the global consensus theorem says that given any initial data, one of possibly infinitely many equilibrium points will be approached. So a way of saying this is, if you think of the freedom this gives you, arbitrary individual differences here and here, in arbitrarily many individuals, it holds for any n, 100 zillion, it's fine, can be reconciled to yield global consensus if there exists some kind of a shared community understanding, the adaptation level. And you're going to get oscillations when you get a breakdown of this kind of understanding. Basically, the hypotheses that go in it, let me just say, you need to have some smoothness. You want your amplification function to be non-negative and have some kind of non-degeneracy. You want to be bounded. You want to be competitive. And what I want, the reason I'm showing you all this is just this signal function B. It can have finitely many hills. Well, what is a hill? Remember, a sigmoid signal had one hill. That's like one random factor. To say you can have an arbitrary number of hills means that I can have a population where there are arbitrarily many cooperating subunits, each of them creating hills, and still it'll converge. So, for example, with the sigmoid, you could have a probability distribution of firing around a threshold. When you integrate it, you get the sigmoid, and when you divide by the linear part, you get the hill. So it's like multiple sigmoids, and this will work for any number of hills. And I can't show you the proof now, but basically what it says is that the dynamics get trapped in bowls from the highest to the lowest peak. So first, the dynamics can only go to the left and the right of the highest peak. Then after a while, the dynamics can only go from the left of the lowest peak to the right of the highest peak and sticks in between. And these sort of dynamic barriers start getting laid down, the oscillations start getting trapped into these hills, and then once they're in the hills, you can show they can only be monotonic. In fact, there's a beautiful example of wing development that Stewie Kaufman developed that is very much like this. There are analogs in morphogenesis. To illustrate that this is pretty far-flung, I just want to remark that this gives you a kind of model of a competitive market where xi is the production rate of the ith firm, p of x is the adaptation level, it's the market price. It's a competitive market because if you produce more, the price is forced down. And then this says that no matter how you choose your own production and savings, and if you compare your production and savings with the market price, and only make more if you can make a net profit, and amplify it with your own personal amplifier, then even if you have a zillion firms, and all they do is read the market price in the newspaper but don't know anything about each other, you'll get a stable market, and every firm will balance its books. So it's a kind of neo-Adam Smith. It doesn't tell you who gets rich. That's different. So if people are willing to play certain cooperative competitive games, they can get some important things like market stability, but they have to be willing to play. Okay, so well, many models do have symmetric coefficients, and they would go beyond the adaptation level theorem because this can be an off-surround that falls off at distance. In fact, Dan Levine, who is here today, and I use such a network to explain visual illusions like angular expansion, tilt after effect, line neutralization in such a network. Well, in order to try to deal with this case, our first effort was to take the competitive theory, and my conjecture was that there were no jump cycles in a symmetric network. But we never proved it. We still don't know if it's true. That would have been beautiful, because it would have shown that all of these symmetric networks with a narrow on center and a distance-dependent off-surround, they just don't have jump cycles, so they converge within. And then you could have perturbed off symmetry, and it still would have given you the range when it was true. We weren't smart enough to prove it, and so we then, instead of doing a Lyapunov functional theory, we discovered a Lyapunov function, which we published before Hopfield, where we showed how, in a system of this form, which some people call the Grossberg model, you can show that everything goes to equilibrium. So this is like the ABCD theorem, because here you have symmetric coefficients that match these off-surround coefficients. So what Mike Cohn and I proved was that given any ABCD system, if you have symmetric coefficients, pretty general amplification function, if you have a non-decreasing function D, then you can write out a Lyapunov function where this helps you to prove that you go to equilibrium because the time rate of change is non-positive, and then you just have a dissipated system. And so we proved in great detail in our paper, which came out in '83, that trajectories approach one of possibly infinitely many equilibrium points, which would be viewed as stored memories. And that was applied to many specialized cases. It applied to the additive case by design, and here is the additive case. Some people call it the Hopfield model, which confuses me because we proved it first and we have a model 20 years ahead, but maybe the history will get straight one of these days. It also includes the shunting model and a lot of other models which the additive model doesn't include. I should remark in passing that it also includes a model that's very important in speech, which is a multiple scale self-similar shunting cooperative competitive net. This is too much to absorb now, but this helps to explain things like the magic number 7 in a deeper way. But the main purpose of my telling you all this stuff is this critical role of mathematical analysis to let you organize lots of different models. it helps you to really think about the field from a global viewpoint. I just want to spend a few minutes saying that there's quite a bit known about oscillations, and this is an area which has now become very much a source of modern research with a great many new results to be discovered. But we already had many examples of standing waves, traveling waves, bursts, and chaos over a long period. Let me just give you a little feeling for what's going on. So I've already commented that if you have symmetric competitive feedback, as in the Grossberg model, you're going to go to equilibrium. But if you can have fast asymmetric competitive feedback, as in the voting paradox, that's enough to give you oscillations. You can also have fast symmetric feedback, but if you don't just have a narrow on center, so you have a mixed cooperative competitive system, so you can have a broad on center, my cone proved here you could get oscillations, purely fast system. But you can get a somewhat different kind of oscillations if you have slow variables, in particular slow inhibitory in the neurons, even if you have a very narrow on center. So slow symmetric feedback can make you oscillate. An interesting example of such oscillations are synchronous oscillations. And there was some early work about synchronous oscillations in studies of pattern learning and categorization. And many of you know the beautiful neurophysiological data that Eckhorn, Gray, and Singer and others collected. And here, I just want to remark that you can have several cooperative competitive interactions that will give you synchronous oscillations. So I don't want to overdo my time here, but let me just say for the purposes of the later lectures that if you have what we call a bipole coupling or bottom-up, top-down adaptive filter expectation coupling, then if you have a network of uncoupled cells which will stay desynchronized, when you put in any of these couplings, you'll get very fast synchronization. And this work was done with my student David Summers. So you can get fast synchronization. And I also want to remark that you can get something very different from that. Let's say you want to consider gate control. So the main point of this is to show how you would organize very different kinds of data. Here are some of the classical gates in the cat, the walk, the trot, the pace, the gallop. And you'd like to know how you can design a motor system that can operate phasically, so I can stand, and also and as an oscillator, so that I can walk. And so what Mike Cohn and Chris Prevey and I showed was that if you take a specialized version of slow, almost symmetric competitive feedback, and you parametrically excite it with a volitional go signal, then you can replicate the walk, trot, pace, and gallop, and get their increasing speed. So again, the main point is, I'm just doing this to help you to see that in 1 minute you can be thinking about vision, in the next minute thinking about motor control. You have to study each of these problems respectfully, but on the other hand, the math can help you see the links between them. It's not just a bag of tricks. In my final 10 or 12 minutes, I want to just say a little bit about associative learning. just to give you a little of that background. I realize I'm taking you for a pretty wild ride here, but I wanted to get a certain amount of background in before we go into other things. So now we talked about minimal modal models. Let's talk just a little about long-term memory and learning. Many people, especially in neuroscience, like talking about Hebbian learning, where the Hebb postulate was that when the axon of cell A is near enough to its site of cell B, then A's efficiency as one of the cells firing B is increased. That means the adaptive weight goes up. But we need to face it that the postulate's wrong. That the adaptive weight would always increase and we either become unbounded or saturate. And it's wrong for a very basic reason, and that's because Hebb chose the wrong computational unit. Hebb chose the unit of a single pathway, but I would claim that the unit of associative learning is a distributed spatial pattern. And so if we have a pattern of activity here, and we want to have the cell population learning that pattern, then some weights have to go down and other weights have to go up. Likewise, if we're doing filtering, adaptive filtering of this pattern, some weights have to go down, some weights have to go up. And I introduced outstars to sample distributed patterns and instars in order to learn these patterns. I'll talk about this in a moment. But you need both increases and decreases in strength for the long-term memory pattern to learn the short-term memory pattern. And here's where, for example, this gated stuff becomes important. So for spatial pattern learning, I like calling it an outstar. We have an input turning on a sampling cell that can then sample a distributed pattern. And it's called an outstar because it can redraw it as an outstar. And I proved, there are a series of papers on this in the 60s, that an outstar can learn an arbitrary spatial pattern. But what is a spatial pattern? That's a situation where the input coming to this border has a fixed relative activity, even though its total activity can fluctuate. But the outstar will only see that pattern when it samples it. So another way of saying it is that an outstar learns the relative activity. So in long-term memory, just like short-term memory, back in relative activities. So it's studying the synchronous part, it's learning the synchronous part of the data. And this was some of the earliest work pointing us to why synchronicity is so important. So pattern learning implies synchronous processing. I just want you to realize that. Then there were a series of theorems showing how you can connect these in all different ways. And even if they're sampling each other, varying from a feed-forward hierarchy to an auto-associator, there are theorems showing how you can have multiple outstars learning in parallel without mutual interference. And that's very important for designing feedback nets. The next stage was how do you do a minimal learning of space-time patterns? And here the idea was simple. Think of a space-time pattern as a sequence of spatial patterns, just like a movie is a sequence of still pictures. And so the movie might be playing down here, and then a series of outstars will sample the movie, and you'll have a sampling signal running from one to the other. What's there, now what's there, now what's there, sample, sample, sample. And so each outstar sequentially samples a space-time pattern for a short interval. And I believe this is an ancient and ubiquitous kind of design. There are examples of this in command cells and invertebrates. But more recently, Mikhail Fee at MIT has just shown that this kind of circuit seems to occur in learning in songbirds. It seems to be what I call an avalanche. So it's really quite intriguing. And they have beautiful experiments you might want to look into that. Well, the next step then is how do you get self-organizing avalanches? You have to have a system where it can discover its own categorizing node through install learning. And having discovered that node, it has to be able to sample the patterns that it's interested in through outstall learning. And then you've got to be able to link these command cells together through a kind of serial learning, boom, boom, boom. And there are theorems about all of these things, which I think are still really quite helpful, and I believe will be very relevant to understanding those songbird circuits. Well, once you realize you need self-organizing command cells, then you have to understand how install learning occurs. So, as I pointed out, there are outstars, where a sampling cell learns a distributed pattern, samples the distributed pattern. By duality, instars have an input pattern, and you have a node here which turns you on, it becomes a category node, to try to learn what is the pattern trying to activate me. So for pattern learning, you have Zij, let's say you have gated learning, and for instar categorization, you have Zji, so you reverse the arrows. And this kind of study, Malsberg and I in the mid-70s were led to put together instars and I did shunting competitive nets, Christoph preferred additive ones, led us to introduce competitive learning and self-organizing maps, which Teavo Kohonen then ran within the 80s, where here you have a shunting competitive feedback net. So we talked about that. That's why I talked about that with you. It can try to normalize the total activity. It can try to contrast enhance the winners here, is what Teavo likes calling a bubble. And it stores it in short-term memory. And when in those stored cells get stored, they can give you trophic feedback so that you can learn in the instar weights what pattern is coming up from the source. So here you have gated learning, gated steepest descent instar learning. And that kind of learning, you can see what the goal is, because the input, as I talked about a moment ago, is the dot product of the activity times the weight vector. And that dot product is just the product of the lengths times the cosine of the angle between the input vector and the weight vector. So clearly learning should make the weight vector parallel to the input vector, makes the cosine go up so you get a more sensitive response, and that shows you got to normalize the input vector. So that's all easy to see. And then in the same period, you could see how by taking this piece, the competitive learning part, and throwing on outstars and training the input and output, you can get what I like calling universal recoding, an associative map from any n-to-m dimensional vector. And this was also done in the 70s, even though the backprop people claimed it couldn't be done until the 80s. Well, I don't want to run so fast over this. I realize I'm going pretty fast here, but all we're doing is putting the pieces together, instars, outstars, shunning competitive net. You can learn an arbitrary map. The question's now going to be, how do you get the most sophisticated categorization here so what you're learning in your readout is good enough to give a prediction? And this is all feed forward, but that naturally led to work that Gail Carpenter and I and many of our students have been doing, and people around the world, when you have bottom-up and top-down and feedback nets. Then you have reciprocal bottom-up and top-down learning, and an adaptive resonance theory that clarifies how you can get self-stabilizing learning, categorization, learning of top-down expectations, paying attention, and other things I'll tell you about in my lecture tomorrow. Well, I mentioned in the minimal modal models that there were also medium-term memory equations, but on reflection, it seemed that it would be easier for me to motivate where they come up, because there are several kinds. And so I'll be introducing them as we go into architectures in future talk. So this is the most math you're going to see from me. Most of the rest will be stories and trying to get you into the principles that have been helpful in explaining a lot of dating, doing a lot of high tech. But I hope I didn't totally fail to show you, if you just follow your nose and ask somewhat different questions. Right now the questions are 30, 40 years old. You were forced into this. It's not like you have to scratch your head. I felt forced into the data. And I'd like you to come away with that feeling, how to get forced into the data. It's not like, oh my God, will we ever understand the brain? I never wake up in the morning without knowing exactly what I'm trying to do. Thank you for your attention. So now there's a coffee break. If people could try to be back by 25 after